Okay, so in this video I'm going to be talking about derivatives, and derivatives are one of the basic things that you learn in the calc class, one of the first things that you learn that can be applied to all different types of things, such as the chain rule and other solving of equations later on in calc. So to start off, start with what in fact is a derivative and how it can be used and how it is denoted. So the boring textbook definition of a derivative, kind of just the word-for-word definition, is the slope of a curve. Or if you want to apply the definition, get a more physical, science-y definition, that would be the rate of change or the velocity. So you may be wondering, how would you signify that something is a derivative, and how do you denote that something is a derivative of a function? So the way that you would go about doing that, if you have a function that would be f of x, let's just say f of x equals 2x. And if you have this function, if you want to find a derivative, you would do f prime of x equals 2. And later on in the video, I'll explain more about why it is f prime of x equals 2 and how you actually find the derivative of a function. So to start off, explaining a little bit more about how you find the slope of a nonlinear curve, here is just a regular x and y axis with a nonlinear curve in the middle. And how would you go about finding the slope of this function? So every point on this function has a tangent line, which is a linear line from which you can find the slope of the curve. So picking any point along the curve, you could pick another point as well. Every point will have an x and y coordinate. From there, you can draw your tangent line of where it will intersect the point on the curve, and finding the slope of this line is how you can find the slope of the curve at that particular point. So here's an equation to find out that. And if you look at the dotted line that is denoted by change in x, and then there's also change in y, you use these different measurements to find out the slope of the curve. So using this equation, you take your function So once you plug in your values to this equation and you find yet another equation, that equation can be used to find the slope of any point on your curve. And in this case, we'll use f of x equals 1 plus the square root of x. So our function is f of x plus change in x minus f of x all over the change in x. So to talk about what that means is f of x plus change of x is your x value, which you would use to find your slope, and then f of x is your y value all over the change in x. So what you're going to do is you're going to plug in x plus change in x for every x value in your original function. And as you can see here, the positive 1 and the negative 1 cancel out, so you can just get rid of those. Once you simplify, you're going to get square root of x plus change in x minus square root of x all over change in x. So once you get that, you're going to multiply both the denominator and the numerator by the numerator, and this is just to simplify to get your answer. So in this case, you're going to multiply what you see above all by the square root of x plus change in x minus square root of x, and then the same thing for the denominator. So if you just want to follow along, I'm just going to be simplifying to find the answer. So one thing to keep in mind when you're using the equation to find the derivative, the change in x is going to become pretty much irrelevant. And the reason for this is if you want to rewind the video and refer back to the axes that I drew before, the closer that the tangent line gets to the point of the slope that you're trying to find, the less relevant change in x is going to be. So basically, plugging in those values and finding how to apply that equation to find the slope took a really long time, but luckily there are other ways of how to find the derivative of a function. And when you're solving a problem on a test, you're not going to want to go through all that because it just takes way too long. So, for example, if you have a function that is f of x equals 3x squared plus 2x, and instead of doing the whole formula that I explained before, f of x plus change in x minus f of x all over change in x, which is just painful and difficult sometimes to plug in values and completely understand, what you do is take your exponent, and so in this case it's 2 for 3x squared, and multiply it to the value in front of the variable. So that would be 6x, and then what you're going to do is from your exponent you're going to subtract 1. So you'd get 6x minus 1, and then the other x value didn't have an exponent with a numerical value, so it's just irrelevant. Sadly, it's not always as easy as that problem. Sometimes you'll have an example that will be something like f of x equals 2x plus 3 squared. And in this case, when you're dealing with a function that has a set of parentheses, it's going to be very similar. You're just going to take the exponent, bring it to the front, and multiply it. So in this case, it would be 2 times 2x plus 3. And then instead of subtracting, well, you do still subtract 1 from the exponent, but that would just be to the first power. And then you're going to multiply by the derivative of what's inside the parentheses. Other times, you may have products and quotients that you need to find the derivative of. And this can seem kind of intimidating, but there is the product rule and the quotient rule, which are fairly easy to understand when kept in simple terms. So I'm just going to stay in simple terms. So here what I've done is written the product rule and the d over dx of uv, and there's uv over there, and just d over dx is another way to denote derivatives. So in keeping things simple, as you can see, the product rule is right to your left, and once you find the derivatives of both u and v, you take your values and plug them in back into the product rule. So in this case, it's going to be 4x squared times 2 plus 2x times 8x, and then you're going to get 8x squared plus 16x squared, and that's going to be 24x squared. And that's how you find the derivative of product. The quotient rule is a bit more complicated, not hugely so. Again, just denoting the derivative by d over dx of u over v. And the quotient rule starts with v times the derivative of u minus u times the derivative of v all over v squared. So in the spirit of keeping things simple, I'm just gonna lay down a function with some pretty simple numerators and numerator and a denominator. So first, just like the product rule, find the derivative of u, and then find the derivative of v, and then plug in your values into the rule itself. So in this case, it's going to be 4x times 6x minus 3x squared times 4 all over 4x squared. And after simplifying, you would get 12x squared over 16x squared, which is equivalent to 3/4. So, you can also find derivatives of trigonometric functions, which sounds really scary and difficult, but it's really not. There's actually a very helpful chart in the textbook, if you're referring to the textbook, on page 149. And in my past experiences on tests, teachers have provided these different derivatives. Some of them are, so like the derivative of f of x equals sine, or f of x equals cosine, and all of that stuff. Here's the nice little chart if you want to look at page 149. So one of the examples would be f of x of sine. If you like to memorize or look at graphically or just refer to the textbook, it would just be f of x equals cosine. Also, in addition to the first derivative, there are second derivatives, which are not difficult whatsoever. So if you have f of x equals 6x cubed, your first derivative would be 18x squared, and then you would do the same thing as before and multiply the exponent by the number that precedes the variable. So thank you for watching, and have fun with derivatives.